Hey, Tony.
Hey, morning, David.
How is your laptop Windows 11 experience?
Currently, no problems.
Oh, nice.
I had to update the BIOS, remove like WebEx, some background apps, and a couple minor things, but it was mostly the BIOS.
Oh,
Found the
wow.
right, once you find the right IT guy,
Yeah.
but
It,
there's three or four good ones, but yeah, you gotta kind of reach out and you get the regular guys and forget it.
yeah.
But yeah, back to normal.
Yeah. Hey, it's same thing with EDA bug reports, right? If
Oh,
you can get
yeah, whenever you get a new release, forget it. Yeah.
yeah.
Yep. Hey, I've been using EDA a lot longer than I've been. So I can relate.
Yeah. Yeah, it's fun, isn't it? Um, let's see. I wanted Singman sent me an email earlier this week about the status of the design.
Who?
So
Who?
Singman.
Oh, Sigmund. I thought you said
Yeah.
Siemens. Okay.
No. Singman.
Okay.
Singman. Uh, so I wanted to see if he would join and talk about that. Or maybe the email was okay. Anyway, let's talk for a moment before we go to the JEP30 XML stuff. Let's talk for a moment about the design itself. So, Tony, we decided to switch back to HBM2, right?
Yes.
Okay. So I'm gonna have to create a bump map for HBM2 then.
Okay.
Uh,
I mean, you have the XY coordinates, right? So you could just use that.
yeah, basically, when I don't know what to do, what I do is I take the HBM signal pins and just put them onto the die side as well, one to
Yep.
one.
Yep. That's the prudent thing to do without having a real phi.
Yeah.
It
Okay.
lends itself to having beautiful signal integrity routes, right?
Yes. Exactly. So I will do that. I will have to update the UCAEs from balls to UCAEs, and we'll use 45 micron pitch. I'll just add one core power and ground um, on the entire
Okay. Yep. Yep.
uh, die, right? Because we don't know any better. We'll assume that any regulation of voltage happens on die. That might be a fun thing to look at to do, but we can
Might
do
be a
that
fun
for next time.
might be a fun thing also to create a simple UPF file.
Oh yeah, for the chip or for the dice or for the entire substrate
The whole design.
with the substrate. Yeah,
Yeah.
yeah. Let's yeah. Before I get to creating the UPF, I'll have to define some connectivity, do bottom side bumps, and any preference what bump pitch you want on the land side, the substrate,
Uh, what side of the substrate? The bottom or top?
the bottom.
Bottom. Mm, I don't know. Uh, um,
We'll use
you could
let's
probably
pick
ask. Um,
let's let's pick a number 800 microns or 1 millimeter pitch.
uh, you're talking about the ball pitch?
No, the bottom of the substrate, the part that attaches to the PCB. the PCB side of the.
That's the ball substrate. That's the ball connection to the pin circuit board assembly.
Well,
And
that's
isn't that the same pitch as
you're talking
after
about
you
the C4 bumps. They're called C. You're talking about C4 bumps, right?
Yes.
Yeah.
I'll probably use something like 800 millimeter or something like that.
800 microns, not millimeters.
Yeah.
800 millimeters might be a little bit big.
Yeah. No. What I said is 800 microns or millimeter or a millimeter.
That I don't know. That seems big. I mean, your ball pitch is either a millimeter or half a millimeter, right? For a substrate. So your C4 bumps.
Yeah. So the C4 bump is about 400 to 500 microns in diameter, right? So
Really?
the pitch. Yeah. Some of those. Some of the CPUs on the market today are at 1 millimeter.
Interesting.
Yeah. If you thought the PCB guys, remember, they are still 20 years, 30 years behind.
So you're saying the C4 bumps and your bottom balls typically are on the same pitch or similar? Because your balls are typically a millimeter pitch, right?
The way I would have done this, David, would be to how many connections are you going to have from the component to the board?
Wow, it's
Not
kind
many.
of arbitrary for this design.
Yeah.
Yeah. Because we right now I think we have 0, but we're gonna have to make some just so we have something.
Oh yeah, you can't have 0, otherwise you have no connection to the printed circuit board assembly.
This isn't a real design, so we don't even have a substrate. So, but for a real design, you would need to do that. So we're at this point, we're not even planning on doing a substrate. We're just doing the interposer.
All right, but the way I would see that you calculate something like this is determine how many bumps that you need to have to the printed circuit board assembly. Then determine the area that you need to have to be able to support the interposer and all the internal connections into the one into the other. Assuming that it's going to be a square chip, you create an array. You try to have the maximum pitch and the maximum ball size that you can fit into that space. That's what you should aim for. But you don't obviously want to go above too high a pitch and too high a bump size. That's the way you should do the calculations.
Right, assuming you have a design that has interface. We don't have any external interfaces at this point, so we could just pick a reasonable number.
Yeah. Okay. So, Tony, what you said. So let's backtrack for a little bit.
There's wasn't that in Sigmund's tech file, the bottom pitch? Because that's something we really should get from him. I mean, they have a real class interposer, so he should be able to provide those numbers, right? Because we really want the we need to know what the manufacturable range is, min max, and then we can pick some in the middle.
Okay.
So hey, Sigmund.
Hey, Sigmund.
Yeah. Hello, I'm late. I'm sorry. Yeah.
Not sure if you followed the discussion here. I'm not sure when you dialed in.
Can you hear me?
Yeah.
Oh, yeah. Thank you.
Oh, okay. No. Sigmund.
Yeah.
Okay. I think I captured your stuff somewhere in the meeting minutes here.
Yeah.
These are materials, dimensions. What is on the bottom side of the glass? What is the bump pitch that you're working with?
Bottom side of the glass interposer.
Mm-hmm.
You mean the C4 bump pitch, right?
Yes.
Yeah. I think I provided in the. Let me check again, please. Yeah.
Yeah, Tony, the reason I proposed these large numbers, I was thinking that this glass is going to go straight onto the PCB without a substrate, right? Not not the interposer with a substrate, but just
Yeah,
the whole
okay.
thing is, yeah. Okay, never mind then.
It might, I don't know a lot about glass interposers yet, but we
Yeah,
will.
so yeah. So the bottom line bump pitch is 650 micrometer, 650 millimeter. Yeah.
Okay.
Okay. Okay, let's go with that.
Okay. Sure.
And do you have preference over inline versus staggered?
I'm sorry, what was that?
Inline bump pitch versus staggered.
Inline bump pitch versus staggered. I think I need to find it. Yeah.
Okay. Okay. Let's do inline. Let's do inline.
Sigmund,
Because
do you actually have like a DRM, a design rule manual for this? Any documentation?
You mean the design rule for glass interposer?
Yes.
Or
Yes.
oh yeah, I think I already provided in the table.
yeah.
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 That's all you have is just that one table? That's the only
Yeah.
documentation that exists?
Yeah. That's everything. Yeah.
Okay.
I found it from the
Okay.
a lot of publications of
Okay.
PRC. Yeah.
All right. You don't have like a caliber deck or anything for this or any?
Yeah.
You do?
But no, I don't have
Okay.
the specific design rules for that.
Okay. All right.
Okay. So Sigmund, with you sent me an email. I apologize, I didn't reply. So
No worries. Yeah.
I will need to update all the design files
Mm-hmm.
with the new HBM interface with UCAE, add power ground, and I will send you those.
Okay.
Should take me we'll see.
Okay.
Best case 1 week. If
Can we,
some
David, can you put down your assumptions here for how you're going to connect to the printed circuit board? So 650 microns as inline. And can you specify how many bumps?
Well, we'll see how big the interposer is, and whatever fits in the interposer, that's how many bumps we'll put.
All right. So if we want to create a part model that represents the entirety of the package, we will also need to know what signals it is that you're bringing out to those bumps.
We'll have that.
Okay.
There will be just a few signals going out, but yeah, there will be just a few signals. The only signals that come to mind right now that are going to go out, apart from the power and grounds, are going to be the HBMs, the direct access pins. Those are the only ones I can bring. UCAEs are going to be contained within the interposer.
Say again, is it the entirety of the HBM2 that will get exposed, or just certain connections of the HBM that will get exposed?
Just certain connections of the HBM.
And you'll be able to tell us which connections they are.
Yeah.
Okay.
Michael, anything with the DA goes external. Everything else is internal.
Yeah.
So they're called direct access. They're used for debug by the vendors. So typically users don't use them. Sometimes they don't even pin them out, but just in case you have to, run some memory tests or.
But I would assume that you'd also have a certain quantity of power and grounds. You'd have clock signals and control signals in addition to the DS.
No, I don't think so.
We'll just have the power and ground.
Yeah, they're just power and ground. You would just spread them out to normal external IO buffers.
So all the DA signals and the power and ground. And how many power and grounds per signal? So let's say if you have a 500 signals, how many power and grounds would you want?
Are we talking about the HBM or are we talking about the die?
You're talking about the component going onto the printed circuit board.
Yeah, so that's the bottom of the interposer. So it doesn't matter. I mean, it's not a one-to-one, right? You've got, many balls, hundreds of or thousands of power and ground microbumps on the HBM and the top side of the interposer. So it's really just a function of power, the power density. So, we'll just put, reasonable amount.
Yeah, Tony, what Michael has in mind is that on the chip side, when you add, you have a requirement of some certain number of power and ground per signal, right? But that doesn't propagate down to the
You're
substrate.
talking about the external IO?
Yeah.
Yeah, that's, you probably just need one, for your IO ring. I mean, we don't even have an IO defined yet, an IO ring. So
Yeah.
now just a simple, just an IO, VDD, and VSS is what you need, probably two. But eventually, I think we should, put some external interfaces, mock up a dummies PCIe. But for now, we're just gonna, just we don't have any external IO, which eventually we would want to do, but it's not a priority right now. Unless you want to, Michael, add a PCIe interface on this, or SerDes or an Ethernet interface.
And we can put in anything it is that you want. But remember, Wednesday we were saying one of the things we will ask for today is the proposed design, so that we can make a part model of that design, because we want to test out how we can automatically load the design rule kits for the various dies and interposers, etc., and show if we can make the connections without having to have a human in the loop to make the detailed level of mapping. So this is the concept we want to test out, and to do that, we just want to mock up its design.
So I would suggest maybe just doing a PCIe interface, right? Just, we're not going to use it, but just it'll be just, a lot of these chips will have that. That's pretty standard out of the box, and that will demonstrate where we can do some routing, external routing.
Okay, but don't you?
That's going to hold up our effort to get a CDMXL model. But if you turn that around quickly, great.
I mean, it's all down to the information that we get. What we get is what we can put into the system. But
yeah, I don't have any footprints of that, so we could probably. Yeah. I don't know if those are standard interfaces.
No, it doesn't look like it.
It's probably not in the spec. I think those are just custom. I can poke around and see if I have anything, but
and at the component level that makes connection to the board, we can make you the footprint.
Yeah.
All right. No, I mean, let's take that as an action to go off.
Yeah. I agree.
I may be able to dig something up. I have to look around. I mean, I have an interposer design, but that has SerDes, it has PCIe, and it has HBM. I can send you that. I need to check to see if I have a. an exit, a CSV file for that. But that's something I can generate.
Yeah. Okay.
Actually, a good person to ask would be Kendall. I'm sure he has something. You want to reach out to Kendall, Michael?
Say again?
Do you want to reach out to Kendall, or you want me to do that?
Make an introduction to me on Kendall.
Kendall.
Oh, from our own side. Okay, we can do that.
Yeah, let's do that. Yeah. I wouldn't be surprised if he chipped that he pulled the UCIe. I would be surprised if it didn't have a PCIe interface or something.
Yeah. Yeah. Let's. Here's the thing. I would say, for this global summit, let's focus on what we can do. I think the PCIe will distract us a little bit from accomplishing what we want to do. Right. Let's get this design set up and done, and then we can always go back and add UCE to it.
Yeah, I mean, maybe you could just. I'm sure we have extra space on the template, so we could add it later, right?
But
Yes.
David, why don't you just give us what your design needs at the end of every week that you give us the actual what you have completed on the design, and we'll just keep in sync with you as we go along.
That's fine.
I mean, how long do you think it's going to take you to complete the design?
So I don't want to commit right now to a specific time frame. Let me take a look first, and then we'll see when I have. So this is the CPU. Right now we have a little bit space for to add PCIe on this side.
Yeah, they're typically pretty small.
Yeah. This will get smaller a little bit, so we should be.
All right, let's move
Okay.
on. I'll look around, see if I could find something, but I would start with Kendall. If you can't find anything, let me know, Michael, and I can do it.
Yeah. Okay.
David, can I ask a kind of dumb question?
Please do.
Yeah. Is there any kind of rules for bump placement? Is it depends on the interface or yeah?
Yeah, so let me attempt to answer that. So in general, to manufacturing these things, there are min-max rules and spaces and dimensions. So there's, from that one perspective, there's manufacturing rules, right? What's the smallest you can build, and generally can go larger, but with some of these special interfaces, some of them have very specific predefined footprints, and they may have different options, fine, depending on different technologies. Like an HBM is standard. There's only one standard for an HBM pitch, so it's fixed. So if so that you're pretty much mandated, if you're going to use an HBM memory, you need to be able to do that. But generally, there's just min-max type rules, and there's a bunch of special rules, like where some of those rules come into play is you have stress. So if you change your pitch, if you do it very abruptly, or you have a big space where there's no bumps, that can create some additional stress. So a lot of the rules are more manufacturing oriented, so you have nice smooth transitions, so you don't have these stress points. So that's the nature of the rules. They're really designed for manufacturability. Yeah. So, at some point we would like to run stress analysis. Probably won't be till next year, but then we could start playing with that kind of stuff and then changing the rules. But right now, we just put something that's reasonable. We're not even looking at that.
Yeah.
Okay. Understood. Thank you for the answering. I was always curious about the bump placement when I see the Davis, the design farm. But
Yeah.
thank you.
So,
Thank you.
yeah.
though.
So those interfaces are very well defined. But, if you're just building a regular chip with regular input and output buffers, you can do whatever you want. But these large macros, high speed interface type blocks, they have a very specific bump pitch on them.
Interesting. Yeah. Okay. Thank you.
Yep.
Thank you so much. Yeah.
Yeah. Okay. Michael, let's switch to JEP30 models that you guys are working on. Any update on that?
Yeah.
Okay.
Justin, let's start off with the presentation stuff first of all, while you're bringing that up. Nathaniel, have you finished the HBM2Es, right?
Yeah, that's correct.
You have finished it, right?
Yeah.
So can you get those files sent out to David?
Yes.
And the UCIe, I believe that one should be finished as well. So Justin, can you bring up the presentation that we created the other night?
Yeah.
First thing we want to do, David and Tony, and is to go through what the files mean, because there's going to be many part model files, and we need to understand what how they're building and nesting within each other. So, Justin, if you can share. We don't see anything yet.
Still loading the PowerPoint. There we go. All right, let me share. All right, it was this one, Michael?
It's the one page that we just did 2 nights ago. Oh, right now I cannot see anything.
This one?
So,
No,
Mike,
we're
the
not
way I'm
sharing
looking at this, there's only 2 port models. There's one for the chiplet and one for the interposer.
Yeah, well, it's I want
And then there will be a separate file that with a format that has yet to been defined to define how those objects, those chiplets get placed, the orientation of those. That is not going to be part of the port model. That is actually part of the 80K. So that's the 3D stack.
All right. Let me go through this slide now here, first of all. So HBM is a standard body definition, right? It's as defined by JEDEC. In it includes both the electrical and the physical pattern. So the entirety of all of that standard, which includes the electrical standard and the IMO package layout, is all contained in one part model file.
Yep.
Right. In the UCIe example, the UCIe standard only specifies the electrical information. It does not specify a physical pattern for those devices. So from a standard perspective, the part model only contains the UCIe electrical.
Okay.
However, when you're going to embed that into a design, you're going to give it a particular footprint pattern. And so what we do is we create a UCIe design instance, which is a second part model. And inside that has just inherited everything from the standard, but now it contains all the physical bumps and the physical locations of those.
So essentially, it's a hierarchical part model for the chiplet, right?
Yeah, but it's not actually a hierarchy. So now you have now you're
it's-
going to take.
So it's not a real hierarchy. So it's a pseudo hierarchy. It's kind of like Laff and Daff. It's not real hierarchical, which makes life difficult. But
You wanted to be able to reference a part model file from the design instance one, and then in the design instance only include the additional piece of information that makes up the design instance.
say, I mean, you have to look at it this way. So when you're building these things, you will be building them hierarchically, right? You have different predefined things, patterns in this case, and then you're going to be instancing those inside the chip. So from a designer perspective, the chiplet designer, as well as the package planning, architect, really is designing this hierarchically. But once that chiplet is done, it's kind of frozen. It's a black box. Then you essentially just have a flattened view that has the pins.
Okay, so let me be clear on this. You would like to have the UCIe electrical as one input file, the UCIe physical, which is the design instance, as a separate file, and the mapping between the two would be included in that physical file. And that file would only contain the physical mapping and the physical bump size and the location, but it would not include any UCIe electrical. And then somewhere when we go through the association, we join those two together. That seems to be our
conceptually, I agree, but the implementation and some of the subtle ways you would do that, I can't answer that. But
all right, okay. So let me continue with the concept here. So there may be other components that are not coming from a standard perspective, and they would be specific design modules, and they could be put into a part model format, right? So you might want to create your own particular module for whatever reason, and now you want to put it into this particular design. Now,
yes. So we call it like pin groups. So you can define a collection of pin groups. So that could be power pin groups and ground and functional. So you want to be able to define a collection of pins as a unit, and or tools support that, or floor planning tools support that. So it really would be good if these formats are compatible and can do that.
All right. So that's another piece.
Because we don't want it to be flat, right? We don't want this to be flat. So we need an efficient way of describing this in a concise manner, right? These detailed patterns, because we're going to deal, someday soon, we're going to be dealing with millions, possibly billion pins. So we need a very efficient mechanism. I think we have that in the format, correct? You did some very
we have that. Okay, let me continue with this because
we need to make sure that we have a path into the planning process where we could leverage that, right?
I think Tony, for now, that's all going to come later on, because right now we're just trying to get the base files ready. I'm not working on the planning to bring it into the tool, so I'm just trying to present the slide here from a pure data perspective. Okay, so let me finish that first, and then we can talk about how it is you want to consume all of this data. For now, I just want to discuss the process of understanding the data, right? So in your design, so we have here specific design modules in part model standard, which is in the green box. You also might get to the right of that custom design circuits that you want to put into your design that may not be in part model design format. So that too might become an input that you have to deal with. On the left-hand side, then you have a whole series of design rule kits. They can be the process assembly design kits for any of the interposer, substrate, assembly OSAT, the test area, the package integration, the PCB fab, the PCB assembly, the PCB test. All of those are going to have a range of different design rules, right? Now, some are going to come from standards bodies and some are going to come from boundaries. And what we want to do is we need to find a way to associate these design rule kits to the various inputs in a highly efficient way. And so what we're proposing is done through this association box. And the purpose of the association box is that it's going to look into the HBMs. And in the HBMs, we have things like physical die size, scribe reference rectangle, active zone, regions. All the regions are pre-generated by the component manufacturer. So in advance, I may not know what those region names are, but I may want to apply a certain set of design rules to a specific region. So how do I go and do that without having to dig through the detail of the HBMs and the design rule kit to identify what that relevant data is? Well, what we think is that given the structure in a very controlled way that the HBM detail and the design kits will be created, we could very easily create a GUI that will pull out from all those files what the various regions are, what the various design rule kits are, and then you allow the person to make an association between this set of rules goes to this particular region.
So when you say we, are you talking about the JEDEC, this working group? Who's we? Who's going to create this GUI?
This would be the well, two concepts. Remember, I said that the design rule kits are some are coming from the foundry, some are coming from the standards body. So for the ones that are coming from the standards body, we should be able to, as JEDEC team members, should be able to associate that this set of rules goes to this particular region or bump or ball inside a HBM, for example. If the rules are coming from a foundry, the foundry may call certain things in their own unique name. And even though we put it into a standardized structure, we may need the support of the design engineer to say, I want this specific foundry rules to be applied to this area in my design because I'm going to use, for example, bonding technology, copper-to-copper bonding, as opposed to some other form of bonding. And therefore, the rules that are applicable to copper-to-copper bonding needs to be applied in that space. So somewhere in the design process, you're going to have to choose the right technology that applies to that specific area so that the appropriate rules that are applicable to that technology gets applied to that specific area.
Yeah, so there is the notion of region specific rules, right? And a very simple example is a corner rule, right? So if there's some of these rules, like you can't have any bumps, 100 microns from the corner. So in order to apply that rule, you have to define the boundary of your whatever you're building, right? So
yeah.
And so those rules only apply if you're within 200 microns. Otherwise, they don't care, right?
All right. Now, there's also a set of rules that come from a foundry which are not compliant with any specific format. And if we are not able to, the box above that, Justin, if we're not able to transform that data into the GEDIC defined structure for hosting the rules, then those rules have to be manually associated to the relevant areas based on what information that you get from an unstructured source. So those on the right-hand side where you have design defined information, this could be difficult to associate because the information that's being provided to you is not coming in a structured way. The information on the left-hand side in the light blue box is all in a very defined structure. And so the preference is always to try and get it in that way, because then the association becomes a lot simpler. Okay, so we're understanding that concept now. What we think we would like to do is we have developed an XML structure for the design rule kits. It's easy to embed within that schema. All of the design rule kits. That does not mean that the material design rule kit and the assembly design rule kit have to be in the same file. In fact, they would probably be in separate files, but they're all conforming to the same schema, which will enable us to do this highly efficient merging of the content together. So Justin, if you don't mind, if we can bring up that schema with the design rule kits stuff, and we'll go through how it is that we have a structured the structure for the rules. Now, as we go through that, we think that the structure we have created can be suitable for any type of rule, be it an assembly rule, a material design kit rule, any type of simple. It's just a matter of simply configuring the type of rules. And I think that what we also need to do is, as part of a standard, we need to make a table specifically of each standard rule, give it a violation consequence, give it a description, show a picture of how that rule is going to be measured. And if we're providing standard values, also we need to provide the relevant limits. Okay, so open up.
Talking about physical rules here now.
Yeah, now we're going to go through the top one, the physical assembly design rule kit. So we start expand a good chunk of this, and then we can start talking about it, right? So the first piece you see in top here is the assembly technology. These assembly technology is taken from the JEP 30. In here we had we merged the SMT and mask reflow together. Paste and hole wave soldering, selective wave soldering, laser, manual, press fit are all to do with printed circuit board assembly and not applicable for the interposer. Wire bonding, copper to copper, hybrid bonding, thermal compression bonding are more to do with the advanced package side. So this then has an ID.
Do you envision extending this to support, or creating a separate branch for chiplets and stuff inside the package?
This is on the left-hand side here, you have the design rule kit. So if you could bring up the part model that shows this design rule kit section underneath that, you can see the relationship between the two. So here on the bottom, you see where the design kit section is here. And by having it under the same part model header, we can leverage types across the top. We can build relationships between one structure and the above structure for the part. So we're enforcing the terminology. But as I said, you are not going to get, it's okay, you may, let me rephrase that. You may not get the assembly rules in the same file as you get the part information. They may be in two separate files. And so we have to test out how the keys and key refs would work in this area. All right, so continue on, Justin, expand it from here. So we've already gone through the assembly. Now,
quick question, Michael. These assembly design kits. What kind of functionality in there is? Can you place objects in the XYZ dimension and rotate and flip and all those kind of placement type? Because that is a part of the 80K that we need to create. That is a separate section of 3D blocks. And
okay, let's come back to that after we describe this structure.
Okay.
And because I think we one of the pieces that we're missing off this is what are the actual rules that we want to put in here, right? So let's go through the structure first of all. So we have a concept of the assembly technology ID, which links to the one above, right? Because we know that the process assembly design kit is going to be different if you're going to do thermal compression bonding versus another type of bonding, right? So the next one then is design classification. And in this, we have, you have the different levels of technology. So are you using standard, advanced, complex, micro? These are the levels that came from the printed circuit board side. We're assuming that you would have different grades of technologies that you would want to apply as well, right?
Yep, correct.
You have
correct.
you have a description and you have a reference document ID. So this could be a URL link to a website, or it could be a very detailed specification that you would also carry with this. Now, we can apply the rule condition. So every rule is going to have a series of conditions, right? And these conditions, pop them all up in there, are going to break up as feature selection, feature type, what's the one below it? Feature placement and feature control, right? And these are all going to become part of the set of rules that's going to be built up. So
what's feature control?
Feature control is, for example, if I'm doing a pad-to-pad spacing, do I want to measure it from the center of the pad to the center of the pad, or the edge of the pad to the edge of the pad? And do I want, if I'm doing it to the edge, am I doing it based on the nominal dimension, the maximum dimension, or the minimum dimension?
Okay. Okay.
So the reason why we're choosing feature control in this structure is because GD&T has this type of structure in there. And so we want to align as close as possible to GD&T terminologies, because that's widely used across the industry.
So essentially, let me just make a comment or a question / observation. So in theory, we can have a set of assembly rules that would be used to define the engineering database, and they're going to assume ideal rules. No tolerances, right? It's just assuming the nominal value for all the rules. But if you had a comparable set of rules, so that set of rules would use the nominal value for the EDA tools, let's say, for creating the database. But when you do the actual assembly on a manufacturing line, you would need that additional what do you call it, feature that would actually be used for the assembly, right? Is that kind
yeah?
of
Yeah. But we did it. We saw this kind of concept of global tolerances in the Intel spec, but the Valor system does it differently. What they have is say that let's say, for example, I have a pad-to-pad spacing, and I have it at 4 is below 4 is critical. I cannot build it. Below 6 is between 6 and 4 is the yield impact area, and above 6 it in the best practice process control.
Mhm.
Now, according to the Intel document, what they do is they put in against these limits plus or minus 1 tolerance. So let's assume then I have 5.9. Well, according to the Intel side, it will be acceptable because it falls within the boundary of 6 plus or minus 0.1. We don't do that here. We say if it's the lowest threshold is 5.9, above which it's going to be a pass, then that value becomes 5.9. Why do you need to have a tolerance? Because what you're doing is you're specifying a limit, a point beyond which, above that, you pass, and below that, you fail. And whatever that limit is, you don't need to specify a tolerance in that rule value. And
Okay.
that's the way the Valor system does it. And it has worked very well for the last 20 plus years.
All right, Michael, we've got 10 minutes left. So this is good stuff. I think we're getting a little bit too deep here. So let's just step back. We have 10 minutes. What else do we need to talk about today?
Can we open up the rule conditions here and let's see what else?
I'm asking David, what else do you need to accomplish today?
So last time, one thing that was left from the HBM2 model is to add the net names to all the pins. If I remember correctly, or that was for UCE. I think UCE had it. It was the pin name, the net names for the pins on HBM that was what was not there.
At the chip level or the internal?
That's the HBM JEP30 model. I wanted to see how that was done.
Yeah.
If it was done.
Tony, we have a lot more questions we need to ask even on this. So do we set up a separate meeting to go through this? Because where do we get the list of rules that we have to make up on? Max has already contacted some people internally, and we don't seem to have a standard set of rules. So there's 2 things we need to have to progress this forward.
What rules are you talking about? You're talking about,
for example, pad to pad. For example, the bump size to the pad ratio. These are just 2 examples. Where do we get the list of those rules? Now we're grouping the rules into certain categories, and we're creating the structure of the rules, but that's just the format. We need to have the actual rules if we're going to standardize them.
So here's the deal. I mean, every foundry, assembly, whatever, has their own set of rules, and we don't have access to that. That's proprietary. Right now, we do have the NAND 40 design rules, so we have those DACs. So I would start there. And
okay, so we need to get a copy of those.
Yeah. So David, are they posted here someplace?
Which rules? I'm sorry.
The technology rules for the NAND process.
For the NAND process.
For the ASIC rules for the NAND.
Oh.
The NAND. What is it? The NAND 45. What's the name of the technology that we're using?
Yeah, it's NAND for it's free PDK 45.
Right. So we have those PDKs. So that would be a good place to start.
We have PDK, but those are transistor level PDKs. They're not that level PDK that will tell you that this is the bump and this is the pad, this is the pad fracture, things like that.
Oh, okay. Are there routing rules?
There are routing rules, yes.
Do they support RDL?
No. Again, the routing rules are again, these are transistor level plus IP level kind of routing rules. But the RDL and things like that, no, it's not a real process.
Okay.
All right. So David, we do not have the experience to identify which these rules are applicable that you want to put into a standard. Some subject matter expert has to work with us now to go down through these particular rules, and this is going to take time. Whether we want to start with a small set or not, We need a subject matter expert to tell us these rules apply to the interposer, these rules apply to the substrate. Otherwise, there's very little more we can do to expand this. The second thing we wanted to do is for us to test out that this operates correctly, we need to build a part model for the completed design so that we can take all these separate files and see if we can go through this association in an efficient way. And so we need to have that concept as well.
Understood. Yeah.
Communicating like this at a meeting, we're rushing it through to try and squeeze it into 30 minutes. This is not the way to figure out the detail now. We need to have dedicated working sessions with SMEs to give us this level of detail.
Understood. That's a different, okay. This meeting is about the test chip, right? And the objectives of this test chip are to demonstrate proof of concept that we can create a part model for a chiplet. It doesn't necessarily have to be the golden part model that we're gonna have down the day. And we wanna start testing the material properties to make sure we can do some different analysis. And we wanna do some very basic, signal power integrity analysis, thermal. That's what we're trying to do with this test vehicle. We can build on that as we need these other cases. As we build out the formats, we're not going to do that with this test case. So I understand what you're looking for. That's a separate meeting.
All right. Okay.
The focus of this meeting is for the test chip. Okay.
All right. So what's the next progress that you'd like us to do here? What is the next step that you'd like us to do here?
Back to the JEP30 models. What's left to be done for the HBM2E and the UCAE JEP30 model?
I believe nothing. It's already we have finished it. The next step is on your side now to implement it into the design.
Okay. You have all the net names for all the terminals?
Net names, no. Net names is a design instance. So you have to take this and merge it into a design. So right now you've only got it from a standards perspective. If you need to make a design instance, you need to give us the design specific information, such as the net names.
Okay.
This is just a set of pins that you have, and they're a floating set of pins. You have to hook them up to something. That's the net list for the chiplet. So that needs to be defined for the chiplet, what those pins get connected to.
Yeah, and that to me is the design part model.
Right.
So we need to have physical location. We need to have the pad sizes on the interposer. We need to have the net list.
Okay, so what I'm looking for is this, okay? When
You ever wanted to see the
I see
what we had showed last week? What we had was under the mapping, like all the terminal numbers mapped to the standard terminal names.
So you have a standard terminal name, which I'm assuming standard terminal name, it, at least the way it's labeled, seems to be the name that's in the standard, right?
Mm-hmm. Yeah.
Correct. Yeah.
Okay. What is the name on the in most of the cases, when that IP is presented as a basically when it's presented as an IP, it may or may not have the same name as a standard terminal name, right? Any vendor is technically free to name it slightly different, right? They may name it D, they may name it D0 or they may name it data 0, right? So there is a pin name and a net name, which is the IP level and chiplet level net name, which is going to be represented on the Verilog boundary, right, in the top module. And then the upper level hierarchy will have a net that connects to that pin. Now, that's the pin name that I'm looking for.
Well, who's going to give you that? Is that something that Micron would give to you based on their Micron names? Because if that's the case, we can take all the standard names, make some modification to it, and stick that into the system very quickly. And you could assume that they are the net names.
Yeah, in most of the cases, they're going to be exactly the same. Right. In the case of HBM, they will probably be the same. Maybe not. I don't know. Right. But in any case, that mapping needs to exist somewhere. Right.
Okay. So we will do that and go back to the presentation document. So that HBM standard will now feed into a component manufacturer instance of a HBM. And once we do that, you'll have that. So that's a very easy thing for us to do. I understand exactly what you want.
Okay.
So HBM's, you're talking about the physical HBM, not the PHY part in the chip.
Correct. Yes.
Yeah.
Right.
So we need our part model, spec compliant pin name in the part model for the HBM, and then for each vendor there will be different, potentially
different names. So that's Justin, that's HBM design instance. That should be a HBM component manufacturer instance.
Yes. Yep. So that is a part model. So the other part model for our chiplet, we're building a custom chiplet. So we'll do a similar thing too. We need to do the same mapping. So we'll give it different names just to demonstrate the point.
Okay. All right. And in the UCIe one, you typically don't have that because you don't have a physical pattern, right? So the UCIe, you take as the standard.
If you're going to have multiple instantiations, those are going outside the chip. By definition, you have to have unique pin names.
You had the standard pin names, but the designer has.
Well, even the PHYs, when you get a PHY, it's the same thing from different vendors. They may or may not have the same pin name. So we need to map those virtual things. We need a mapping mechanism, because eventually, this ideal, UCIe pin map that we're placing down, eventually that'll have to be replaced with a real piece of IP from a third-party IP vendor, and their pin names will vary. So we just need to map whatever they call on their IP to our standard quote unquote pin names.
So
are you that mapping for these virtual parts inside the chip as well?
So can you have these net names even though you don't have the physical pattern?
Yes.
Pin names.
All right. Okay. So what we need
pin mapping first.
Okay. So what we need to do, Justin, is where you have the HBM component manufacturer instance, you need to create one of those in between UCIe electrical and UCIe design instance. And then that will solve that problem. Did you understand?
Hey guys,
yeah, I think so.
I'm late for my next meeting. Can we just wrap up here? I need to go.
Yeah. So Michael, just
David, is there any chance that you can hang on and we can close out?
I'm late too.
Okay.
I would suggest we just add whatever way you think, if you know how it needs to be done, just add the pin mapping, just give it the same pin names. We'll use that, and that should be fine.
Yeah. Okay. That's very easy for us to do. Okay.
All right.
All right. Thanks, guys.
Thanks.
Thank you.
Thanks. Justin and Nathaniel are the Siemens guys. You guys hang on, and we'll just go through this here. So
should we go over to Teams to get off their recording?
Oh, right, yeah.
Okay.
Okay, we'll just, I'll set up a meeting on Teams.
Okay.